Okay, let's start. And first of all, who is ZoomAFM.com? Again, we are former employee of Agilent Technologies. Myself, application scientist. Steve Raba is service engineer. And Xiu Chan is technical manager. Jerokata from Europe, and Louis Pachenko, they're application scientist and engineer in Europe. And the goal for us to be here is to support the Agilent instruments for the next 10 years and then prepare and then teach you how to use your instrument. These are the couple of websites. Nanocube Technology, you can see a lot of my accessories that I invented for the instrument. OnQ is the service website, and then we unite at ZoomAFM.com. So this presentation will be on tapping mode resolution improvement. So one of the difficult things about using atomic force microscope and achieve good resolution is because of there's many variables in operating the entire instrument. For example, here are a couple of variables we can think of. First of all, sample preparation, and then we need to choose the right imaging mode, and need to choose the right cantilevers, and then you need to decide the right parameters. In terms of parameter, there's many things that here we have drive and set point, and then when you optimize your feedback, you have to deal with gain, the I gain and P gain, and there's scan speed and scan size. The difficulty of such combination of parameters is because there are total combined variables. If you put all these together, there's huge amount of combinations. So if you enter a situation where that you try to decide what is the parameters, there are too many things to choose. So we have to narrow down the parameters so that we could reduce the time we spend on optimization. Here's one example of one single parameters allow you to see a sample on a completely different image. This is we call S-layer, which is a bacteria. It's kind of bacteria, and this bacteria will attach itself to a substrate using certain protein molecules. And by changing the scan size, the image looks completely different. You scan the larger size, you see those bacteria. When you scan small size, you can see those individual molecules. So here's the rule of thumb, that if you want to image something, and then how do you decide the scan size? So firstly, you have to ask yourself, what is it you want to image? And what do you expect to see? And then ask yourself another, it's how big is the things you want to see? How big is the species? If you want to see single atoms, then you have to scan no more than 20 times size of the atom. If you want to see the molecules, again, 20 times. And if you want to see a bacteria, which is, let's say, 5 to 10 microns, you have to scan 5 to 20 times the size of this bacteria, which is microns. This is the first thing to decide, is how big is the scan size. And there's many other parameters. In this case, some of the very important things are, for example, drive and set point. Set point, people adjust this a lot. However, I have yet to see anybody actually actively adjust the drive, because drive in a tapping mode imaging is not something that's obvious right there that you need to optimize. However, to my experience, drive is very important. Okay, so tapping mode, we bring the tip close to the sample, and when tip and sample is at certain distance, sub-nanometers, for example, and what you see here is actually the attractive force tip is going to experience first. As you bring the tip close to the sample, the attractive force turns into repulsive force. And how do you manipulate that? Because if you look at the AFM image on its parameter panel on the computer, there's not a single parameter there says force. So yes, we talk about force a lot, but you actually don't know what is the force. You have to make a judgment on your experience. What is the force? And we're going to try to simplify this task in the next 10 minutes. So, okay, let's take a look at what happened when tip is sample engaged. The cantilever is vibrated using a drive, a piece of piezo, and some of the imaging mode using a magnetic field too. You can do magnetic drive too, magnet. When you drive the tip to oscillate, the cantilever will oscillate at a certain resonant frequency, and this resonant frequency is determined by its spring constant and its mass. However, in the reality, the resonant frequency is not only determined by the spring constant of the cantilever, but also is determined by another factor. It's called damping. We're experiencing damping from the surface and from the environment around. This damping can shift the resonant frequency. So it's going to go lower and then shift to the left. But in reality, it's not that simple again, because other than damping, the sample is also experiencing an attractive force to the tip. Yeah, let's take a look at this attractive force, repulsive force curve. Look at the red lines. That as the tip sample and the decreased distance, it will experiencing attractive force, and this attractive force basically adds a negative spring or pulling spring from the cantilever. You know, the spring constant of the cantilever actually is reduced by this attractive force and force gradients. The force is never a constant, it's always a gradient. And as the tip get into the repulsive region, it adds a positive force or push spring to the tip. So the spring the tip is experiencing increase is its spring constant. So it's getting decrease and increase. Okay, so this decrease and increase will impact the resonant frequency for sure. And this is how the resonant frequency will change. When tip and sample gets to the net attractive, the resonant frequency shifts to the left. And when it's experiencing repulsive, the tip and sample shift to the right. First and right first. Now we look at the two lines below, which is a phase curve. And the phase curve will shift to left, shift to the lower, and then they will shift to higher. So, in other words, we could suggest that if you look at the phase image, phase signal channel, when you see the phases shifting negative, you can probably conclude tip is experiencing an attractive force gradient. And when you see the phase shift to the right, you can probably suggest that tip is experiencing a repulsive force. That's great. Now we have some idea of the force. Okay, so as the tip is oscillating, approach the sample. This is a simplified curve that your amplitude is actually decreased. We can put a set point there and maintain the amplitude at a certain set point, and therefore you could actually control the feedback. So the amplitude will decrease at tip and sample getting close to each other, and put a set point there. Now, this red line is some type of phase curve or phase distance curve. You can see actually the phase is in a certain region decrease and then increase. It does not always look like that. It depends on many factors. But when you typically oscillate your amplitude at a certain amplitude, that's for example 20 nanometers up and down, this is going to be the phase you observe. And from the previous analysis, we can suggest that the tip from here to here set point, it is on a attractive force. And from here below 50%, it turned into repulsive force. Okay, now we know how to control attractive repulsive force by play with What is this? Set point. Now, this is a series measurement on the cantilever, and then these are on the right upper hand side. This is what we call the phase distance curve. Then no, this is amplitude distance curve. The one below is phase distance curve. And these different colored lines represents you oscillate the tip at various different kind of resonance, different amplitude. The one on the lower is low amplitude, high is high amplitude. So we run this experiment at below 5 nanometer oscillation to all the way to 25 nanometer oscillation. Red one here, as you can see, for a very long range from here all the way to here, the phase experiencing a big dip of negative shift. And as we drive the cantilever at a higher and higher amplitude, in this case, the blue line, very close to the end, if you move here, the phase immediately shifts to positive. Okay, what does this series measurement tell us is that if you drive the cantilever oscillate at a very small amplitude, for example, in this case, 5 nanometers, compared to you drive the tip at a high amplitude, in this case, 25 nanometers, you can actually change the region of your set point associated to attractive and repulsive force. It's that if you oscillate the tip at lower amplitude, you can manipulate your set point in long range. It's always attractive force. And if you change your drive to a high amplitude of oscillation, and then they just play a little bit of set point, immediately turns repulsive. And this is understandable. If you oscillate tip high amplitude, the tip is oscillate up and down at a higher energy and higher power. When you see that, the tip is going to have more energy dumped to the sample, and therefore it applies more force to the sample. It's just different view of it. It was an experiment, and then this here we oscillate tip at 1 nanometer, which is a very small amplitude, and then we control the force mostly at attractive, and then as you increase the amplitude, it gets more and more easy to get into repulsive. At 48 nanometers, it suddenly jumps into repulsive. Different cantilevers will behave differently when you oscillate at different amplitude of driving, and also the size, sharpness of the tip also matters. Okay. So remember, if you look at your most of the manuals or most of the driving software of your AFM, and if you click auto tune, when you do auto tune, the driving frequency always ends slightly left shoulder of this peak. And this is actually determined by the parameters on your software. It says negative 0.1 kilohertz of shift, and you click that, it automatically chooses a peak on the left. And that's because that's to assure that, and this setup is to assure that when you approach tip and sample, tip will engage the sample at a firm repulsive region, and that make your image a little bit more easy, and no other reason. And does it give you best resolution? No, it does not. If you want to have the best resolution, you have to understand and manipulate the situation so that the tip and sample engage with each other at a certain repulsive attractive force where it's best for the particular sample. I will not even tell you which is best, because I don't know which is the best. It's sample dependent. So, in other words, in some situation, you do want to put your driving frequency at the peak of the resonance or slightly to the right of resonance. When you put the right of the resonance, imagine that when tip and sample is experiencing attractive force, the peak shifts to the left. When peak shifts to the left, the amplitude decrease and your feedback kicks in. The feedback started to be effective. And you're engaging tip and sample in attractive region. You can also put on the very peak of it that also have this effect. And if you put on the left shoulder was high amplitude, it'll guarantee on the repulsive region. And that's how you manipulate attractive and repulsive force. Okay, this is a very smart experiment, and actually tried to measure this attractive repulsive force in a real experiment. Here, the first line is the amplitude resistance curve. The second line is a phase resistance curve, which we can measure. The third line is something unique. The third line that this scientist, Dr. Huang and Kevin Kohler, and what they did is that they actually did tapping engage on using one cantilever on top of another cantilever. They used the first cantilever to manipulate the amplitude and the set point, and they used the second cantilever to actually measure the deflection force, so actually measure the force. And so the third curve here is actually a force measurement, the actual force. And then if you compare the third line to the second line, they mimic each other. And that's further proof our point is that you can actually look at the phase versus distance curve and then measure, understand the force. And that's only true when the set point is at the first, let's say, from 100% all the way to, let's say, 40%-ish. And when it's below 40%, 20, 10%, the situation no longer true, right? It becomes more complicated. So we always try to avoid to lower your set point too low. When it's too low, the force is no longer under kind of like under control, basically. Yeah, it gets more complicated. Some graphics, and then if you put the force frequency below, and then you engage is much more tight, and then you're actually guaranteeing a repulsive force, because if you look at the phase, it's mostly up. The force is also increased. But if you put the driving frequency on the right shoulder, the engaged force and pore force is actually separate. And then if you look at the engaged force, at a certain set point, the force turns to below zero, which is negative. Phase is also turning negative. And then because of separation of the push and pull, there's certain unlinearity here, which make a situation a bit more complicated. And then also sometimes the tip sample engaged is not very stable. Okay. So this is a very simplified view. It's way too simplified. That if you use a small amplitude, in this case red lined, in the large range of the set point, and you're experiencing attractive force or negative force, and if you oscillate tip at a higher amplitude, in this case 50 nanometer, 100 nanometer, when you manipulate the set point, the force increase. The higher the amplitude, the more force will increase. Okay. If you have this in mind, then we know how to manipulate the force from attractive negative force to positive. We need to manipulate one parameter, which is called the drive. This is one experiment that as you increase drive, you can see this color represents phase. As you increase drive from low to high, your phase is shift from negative to positive. And even get into a bistable situation where the tip experiencing the repulsive force at the top of the grain and the attractive force between the two grains. And this is a polymer sample. Polymer sample has a relatively long range attractive region. Here is a video I made. Yes. So this is the same sample. The difference between these different images are the difference in drive. You see, the image looks different. Turn the drive from low to high. Yeah. Even the image looks different. And that's because the sample, because Atomic Force Microscope imaging does not look at your sample. They actually push on the sample and touched it. It depends on how hard you touch. If you have a light touch or harder touch, the sample will behave differently. It's like you lay out some golf balls on a mattress and then you put a blanket over it. You use a small force, you can sense the fibers of the blanket. High force, you actually sense the golf ball below the blanket. By manipulating the drive, you're touching the sample from light touch, increased force, to high force touch. So I put this here, drive. You have to pay attention to the drive. And then most people don't pay attention to drive because they click that auto tune, the drive is automatically determined. And they're thinking, oh, because the drive is automatically determined, it must be a very good drive. This is actually not very true. You have to pay attention to drive. And then the automatic tuning drive, if you put a target amplitude to be very high, for example, if your full range signal is 10 volts, you put target to 8 volts, your drive automatically turns very high. And if you put 1 volt, drive automatically turns very low. So you can adjust the drive before the tuning by manipulate it. But drive can be changed after you finish tuning your amplifier. It's high drive, you're hammering something, and when it's low drive, you're lightly touching the sample. Okay. What's the harm of high force? High force sometimes give you high resolution when you're imaging something, for example, a polymer. It allows you to see the substructure, which I just showed you, those fingerprint type of image. But then it also hurts your tip. You can make a tip a little bit more blunt. So you need to protect your tip. And then to achieve the best resolution, basically you cannot make your drive too high. That's because your tip get dirty, contaminated, or get blunted. And after you determine what the drive is, and you can manipulate your set point and so on and so forth. And then next thing is to optimize the feedback gain. Here's just oversimplification of feedback gain. I put out the mathematics formulas of feedback gain, but this is more visual. High gain means your feedback is getting more oscillate, faster response, and low feedback gain, your tracking is sluggish. Ideally, you increase your gain until it's got oscillation and decrease the gain until the oscillation is gone. And that's the best. Okay, so again, we're back to, we still have a lot of parameters to adjust. How do you optimize the parameter? Here's a sequence you do to assure that you start with a lower force and gradually increase the force. You start with small drive, and then you manipulate your set point from higher to lower. Okay, and then you find the best gain by manipulating the gain. Get your best data. If it's not good enough, increase your drive a little bit. When you increase drive, be careful that don't just increase it. You have to increase the set point so tip and sample is separate, and then you increase your drive a little bit, decrease the set point until tip and sample engage, and then you find the best gain and repeat. So your drive can be, let's say, have 10, 20 different drives. I'll give you an example. If you, after tuning your drives is, let's say, 5, and you withdraw a little bit and you reduce your drive to 0.5, and then 1 and 1.5, and so on and so forth, until you have best resolution. Today, we're not going to have instrument demonstration. I'm not ready for it. Next week, I'll show you the control panel of the instrument. In the much larger picture, and when you're facing more variables, for example, samples and parameters and tips, this I will cover in the future episodes, is to choose a standard sample. and then choose the imaging mode and choose the tip and choose the right parameter, which is the circle I just showed you, and sample prep and so on and so forth. And then through these step-by-step approach, you would reach your best resolution. This is just one example of this, one of the examples of optimizing the image on the center lower. This is the image of a protein sample. And then if you don't have the sharpest tip and if you don't have the good parameters, this sample looks like the image on top, on the top, which is the same sample. And the sample concentration is too high. That's 1 and 2. They all look like circular dots. And scan size is a little bit too big. So when you see something as circular dots, there is a reason. One of the reasons probably your tapping force is a bit too high. So you're squishing your sample. And also possibly your tip is no longer sharp, and so you don't see any substructures. And we used from low to high approach on the drive. You can see the substructure of this particular protein, and then you can see the foldings and kinks and twistings of this protein molecule. Okay, and that's about it. Next week, we will have some hardware time. I will set up my instrument. So I'll show you what I was talking about today. Set up tapping mode, optimize basing parameters. And then next week, we're going to have a demonstration of controller calibration. We'll hook up with voltmeters and Raycar box, and then carefully calibrate the instrument. So look for us next week. Thanks for the members, OnKill and CSI. CSI, they basically built a controller that can drive the Agilent instrument and also some other old instruments. And then here's a little commercial here that in March 30th, Thursday, March at noon, CSI will sponsor, and they will run a webinar using their controller to run multimode from Vico and Bruker, and then run also Agilent. And I will email out these invitations if you're interested. And that's about it for today. Thank you for your time. And if you have questions, please unmute yourself and speak up, or you can also type your question in the chat. And thank you.
Hi, Song. This says it's going to be at noon. Do you have a time zone?
Yes, I have time after this, yes.
No, do you have a time zone for when that noon presentation is going to be?
Oh, I forgot to tell you. This is known as EST, which is 6 o'clock on the Central Europe time.
Thank you.
So you can -3 on your side, yeah.
Hey, Song, it's Jason here. I guess I'll be the first to ask a question.
Sure.
How much does the water layer come into play with the tapping mode and trying to optimize? Because I think I remember reading somewhere where using like the low amplitude kind of keeps your tip in the water layer and it helps give you better resolution compared to like a higher amplitude that might be jumping in and out.
Yes, this is a very interesting aspect of this tapping mode. So the first presentation I showed a force curve using a contact mode, and then when we do force curve and so on and so forth, there was a very large port force. Okay, and then there's no straightforward explanation other than yes, there's a water layer, and then later on other forces can also be possible because of the attractive force or intermolecular force. So yes, there is a water layer. But has anybody actually seen that water layer? I have never seen a water layer because it's just not visible. So using water layer is a very good explanation of what we have been observing. So yes, let's say we assume there is a water layer and a certain thickness. So when you manipulate, you're in the attractive region, and we believe tip is actually in the water layer. And then that's and so on and so forth. But I would like more describe it in a way such that it's actually not a water layer, but a layer of attractive force. It could be water layer, it could be something else. Yes, and then if you are imaging in this region of attractive force, and tip is actually have a certain separation distance, and then it's actually imaging in the water layer, and so on and so forth. And then when you're not imaging in this region, let's say using very high amplitude, tip is above the water layer and hammering down into the sample through the water layer. You can also describe that. It's very visual, but I actually have never seen any way to measure this water layer. I think there is a way to do that, is that I don't remember anybody has measured the contact mode force curve in UHV, ultra vacuum. When it's in UHV, if this force, adhesion force, is caused by water layer, there should be absolutely no attractive force or torque force in UHV. That's one of the things we could test this theory. Another things about this water layer is that this attractive force actually disappeared when you are imaging using contact mode inside the water liquid cell. So in other words, water is everywhere, and there's no water layer, and your attractive force should disappear. That's sometimes also true, but sometimes I observe attractive force even it is imaged in liquid, let's say water or ethanol. So the attractive force is not just the water layer, but there's other forces play a role too. For example, electrostatic force. For example, if you're imaging in liquid, you have a OH bound on the sample, and you have OH bound on the tip, and you do a force curve. There's still a pull-up attractive force. That's obviously not because of water layer, because it is in the water, or in the liquid. It's just a different way of seeing it, and then it's consistent with all the observations. That answer your question?
Oh, yeah. Yeah, thanks.
Yes, if possible, we should run an experiment. Let's cool down the sample. Remember, I showed a image of topographic of a piece of ice. So it's an ice, and then no longer water layer. I forgot to measure a force curve. Otherwise, I can tell you is that water layer, because the test sample is negative 20 degrees C. There should be no water layer.